So attention is basically a very basic idea which is very common in humans. For example, if you look at when you are looking through your eye at a scene, it's not that you are paying attention to all parts of the image with same level of attention. So for example, giving a comparison to, for example, when Arjuna was looking at the fish, right? When he was aiming the arrow, he was very clear that I can't see anything other than the fish's eye. So he was very clear in terms of focused attention on one part of the data rather than on the whole data. So it is this particular issue of when you want to look at a input, it's not like you're looking at all parts of the input with the same attention level when you're generating the output. That is what gave rise to this models known as attention networks. So the idea is, even in the image or in the text, like in machine translation, it's not that you're looking at all parts of the data with same attention. So what you typically do is you focus on a certain region of the image with high resolution, while some other parts get into low resolution. Same way, you may want to change the focus as you go forward by moving your resolution, high resolution point of attention as you sweep through the data. Same way in translating from one language to another, as you move from focus from one target word to another, the focus words in the original input change. But it is not that it is one-to-one, but it's probable that there is some influence of the other words also, but there is higher focus on some parts of the input data. So it is this notion of attention, which is you can think of as a disruptive concept, which has come today as a savior for several categories of sequence models, especially encoder-decoder kind of problem statements, or problems which are related to moving focus of attentions, which has given a new area within deep learning focusing on attention models in deep neural networks. So if you see here, like the example I gave you, here it is possible that when I talk about a translation, and output may be having many-to-many translation from source to target. So when you're talking about the dependence of Y1, it may be that it is dependent on two of the words in the original German word more than the third word. Same way, the source may be dependent more on the one of the words in the original German word. But it is not that there is direct 1:1 mapping like a sequence-to-sequence model would want you to predict. So this gives rise to the notion of attention. Means when you're talking about outputting awesome, there is more attention on some words as compared to the other words in the source sentence. Same way, when you're outputting sauce, it is more related to more specific word or words in the source sentence as compared to others. But it's not like it is 100% derived only from one word, as an encoder-decoder model would want you to believe. So attention is basically the mathematical extension to encoder-decoder model, which says, if I consider the total attention to, say, one output word awesome as 1, out of which, say, 0.1 may be coming from one very small word, but remaining 0.9 is coming from 2 or 3 words, 0.5 or 0.4 from other words. Or if it is coming 0.99 from one word, it's as close to 1:1 mapping. So what this kind of a mapping of attention in addition to the encoder-decoder gives is the focus point in the input corresponding to the specific point of attention in the output is what is termed as the attention model. So it is basically unreasonable to assume that we can encode all the information about the potentially very, very long sentence into a very single vector and then have that decoder produce a good translation based on only that, because this kind of a single vector assumes purely 1:1 mapping between the encoder data and the corresponding mapped decoder data. It is, however, very difficult to extend this to very large range dependencies, long range dependencies, where suppose you're depending on something which is very far off from your current position. So this is actually a problem when you have languages where positional dependence is not so important. So that becomes a problem because you may say the karta first and then maybe say current later, and then you may say karm later. So if you see, sometimes the order independence also makes such a thing very, very difficult. And in general, LSTMs are very good at mapping 1:1 like an encoder decoder, but such architectures where long range dependencies or many to one dependencies where one part has relative focus on one other part of the input, these kind of problems are not easily dealt with in 1:1 encoder decoder architecture. So what is done is, in place of the typical encoder decoder architecture, which is where we develop an intermediate fixed length intermediate model, we use something known as attention mechanism. So what the attention mechanism does is we allow the decoder to attend to different parts of the source sentence at each step of the output generation, so that that attention function, which we give higher weight to one part of the source sentence as compared to the other parts, as we continue to generate the continuous output. Ultimately, we learn the attention function, which is basically the function which is allowing us to map the input sentence to the dynamic output. So what ultimately we learn is what the model has to attend to in the input sentence and what part of the already generated output it has to pay attention to. Both of them decide on what should be the next output. So you need to look at all of that from a perspective that I will not be in a position to give exact mapping of output sentence or output word to an input word. Instead, I will be able to continuously keep on generating the output sequence by learning the attention function between the current output and the parts of the input and whatever is the learned output till now. So that together gives you the output function which is continuously emitting the target output.